Hi, we're Team RoSE, and I'm Kobe, and I'm a part of GNC.
I'm Seth. I'm the lead of Avionics.
I'm Patrick, and I'm also a part of GNC.
So Team RoSE is split up into multiple sub-teams, and we are competing in the URC challenge. URC has 4 main missions, and we are designing our rover to complete these 4 missions. One of those missions is a scientific mission where we collect samples of soil to detect life. We then have the extreme delivery mission where we have to travel at least 1 kilometer out, and we will be delivering a item to an astronaut that's over there. We then have the equipment servicing mission that is about 0.25 kilometers out. And in that mission, we are to do tasks on spacecraft and instruments. And then we have the autonomous navigation mission, which is us traversing through the terrain that is 2 kilometers out, and we're going to get to a certain point that they set at that time.
For materials and methods, the basics you need to power a rover are a battery. Our battery is at 645 watt hours, and it's enough to power the rover for 2 missions. The fuses are meant to protect the motor controllers and logic devices and computers. And our power distribution is equipped with a 12-volt and a 5-volt output at 3 amps each.
The ground station uses GitHub and Jira for project management, uses GitHub for version control, and uses Jira to practice agile software development. The front end of our application uses React and Bootstrap. Our backend uses Node.js, and we use Docker to containerize our application. Down below is a flowchart. As you can see, our application and our rover is connected through a RoSE package called RoSE Bridge. So with that, they're able to create a handshake, and we're able to send information and receive information back and forth.
For autonomous navigation, we use YOLO and we use point cloud data. We use the Z Mini, which creates our point cloud data. And then YOLO is used for object detection, so we can use that to detect water bottles and orange mallets. We use point cloud data for a localization, but there is another purpose we're going to use, and I'll discuss about it in our results. In communications, we're using 900 megahertz for communication for long distance. We are using 120-degree sector antenna for ground station, and this allows us for a grand area, so we can do a point to multi-point connection. We're using 6 dBi omnidirectional antenna, so we can receive those signals and send those signals back out to our ground station. And then we have a 2-rocket M900, which converts our Ethernet to a 900 signal, so we can have it connect from our Ethernet to our antennas.
So this is a power diagram. On the left, you have the battery. Next to that, you have the PDB. Way on the right, you have the motor controllers and motors. Below it, you have the main computer, the cameras, and the Raspberry Pis controlling cameras and motor inputs. For the data portion, we have action commands going to the motor controllers, feedback coming from the motors. The RPIs are giving these commands and receiving it from the Ethernet hub, which is receiving it from a transmitted signal from ground station.
Our ground station is an upgraded version of our previous ground station, so that the user interface is a lot better for operator controls. For example, we reduce the amount of navigation and increase the amount of operator function, the things that the operator can do, such as pop out of view or remove a page. We also added more functionalities and buttons to help communicate with our backend and RoSE.
So for auto navigation, we have started working using SLAM to detect our orange mallets. Currently, we're miscategorizing them. As you can see, it's detecting it as a knife. We tried training the data set with Object 365's data set, which is over 3 million images. And turns out that it's just too large, so we can't train it currently. So we're going to change our methodology, and we're going to use point cloud data to key out the foreground and our background. And then we're going to from there key out the colors, so we can just detect the orange mallet and our water bottle later down the line. For communications, we simulated for the terrain of where we're going to be, and we're expecting to hit 85 megabits per second in speeds, and we're waiting to get the new equipment to actually do real life testing.
To conclude, with a few more testing and feedback, as our rover reaches completion, we're soon able to slowly integrate our software and hardware components.